Okay, so this time on question 4, we're actually measuring a reaction and looking at a reaction, but this time we're monitoring the reaction as it proceeds through a singular reaction. So not just looking at the end point of a reaction and seeing how long it took, we're actually measuring something during the reaction and seeing the amount of one of the reactants, A, as it decreases during its actual reaction procession. And the first question is asking us to calculate the rate of reaction at exactly 50 seconds. So 50 seconds is there. And in order to do that, we have to draw a tangent to the curve. And so to do that, we have to draw a straight line, which is going to touch the curve at 50 seconds and be a straight line as so. And then what we have to do is calculate the gradient of that tangent that we've just drawn. So we'd have to calculate the change in y and also calculate the change in x. That will then give us the gradient or the rate of reaction. So the rate is going to be equal to the change in y divided by the change in x. And so we can use your graph. Obviously, you'll be able to use your graph and look closely at the scale. But we've got a change in y value of something in the region of 0.97. And we've got a change in x of something in the region of 153 seconds. And that's then going to give us a calculated value, which we'll round to, as it says, two significant figures, 0.0063. And then we obviously need the units. So we take the y unit and divide by the x-axis unit. That gives us the units of the calculation that we've just done. So that's moles per second in that example. The second question is then asking us to do the same thing, but this time at 200 seconds. So use a different color. We'd have to then draw a secondary tangent, this time touching the curve at 200 seconds. And so we're going to go something like this here. Okay, something like that. And then that's going to allow us to do our change in y by our change in x. And again, using the graph, you plot the graph and use the values that you can see on yours, but we'd be using something in the region of 0.45 and dividing then by something in the region of 340 seconds. And that's going to give us a value again, rounded to two significant figures as 0.0013 moles per second, same units as last time. Okay, and what we can see is this is now a smaller value than we had in the first one, which makes sense because the reaction is going to slow down as that reaction proceeds. This is then what the second question is. The third question is asking us is describe and explain with reference to collision theory how the rate is changing. So as we've just said, the rate is going down. So the rate is going to decrease. And the reason for this is the concentration of A is also decreasing as the reaction proceeds, because as particles A react with, let's say, particle B to make C, then as particle A gets used up, the number of potential collisions, the frequency of potential collisions that can occur between A and B are less because the number of A particles is starting to disappear and decrease. And so as a result, the rate of reaction as a result of the rate of collisions will also decrease.